Our first presenter is Trey Carroll of North Carolina DOT, the Structures Management Unit Project Engineer. He is involved in policy development, manuals, standards and specifications, and asset management. Please help me welcome Trey Carroll.
Appreciate the opportunity to share this morning. It's the first time I've been to one of these conferences, and I must say it's been a great learning experience. It's really great to see the different DOTs as well as the vendors, and I've taken a lot away from here, so thank you. Tim, especially last night, I enjoyed your presentation. As a NCDOT employee, there was a lot of things you shared that even I didn't know, so it was just good to kind of get that history lesson, so appreciate that. And of course, the food was excellent. So today I'll be sharing the Harkers Island Bridge Replacement Project. We're currently underway with the construction of this. We're the first year in, and the new technology that I'll be discussing is our use of carbon fiber reinforced polymer strands, CFRP strands, glass fiber reinforced polymer bars, GFRP bars. So it's not necessarily a new technology. It's been around for a number of years, but it seems like here in the last 5 to 10 years, it's really starting to gain a lot of traction. And I know for us, this is really the first project where we've implemented it throughout the entire structure. We do have some experience, whether it be research, but also installing GFRP bars in bridge decks. So today I'll be sharing that. And so for those that aren't familiar with the FRPs, the advantages are the superior corrosion resistance, the high tensile strength, and the lightweight. So just to give you a little background about Harkers. So for this project, all the cast in place concrete will be reinforced with GFRP bars. All the pre-stressed concrete girders and pre-stressed concrete piles will be pre-stressed with the CFRP strands. So for the girders, we actually gave the contractor the option to go with the CFRP stirrups or GFRP stirrups, but for this time the contractor elected to go with GFRP stirrups. To give you a little idea of where the project is located, again, I'm sure you guys have seen enough maps of North Carolina the last few days that if you don't take anything else away, at least you'll know the geography. So here's the eastern half of the state. Obviously we're here in Raleigh. Harkers Island is located about 3 hours east and is located near the port of Morehead City and the Cape Lookout National Seashore. For us, this area is considered highly corrosive. So the use of a non-ferrous material really is a primary candidate for using this material in order to create long-lasting structures. So you see here, zoomed in on Harkers Island, it is a relatively remote area. It's home to 1,300 people. It's bordered by 2 inlets and the barrier islands. As part of the project, we're replacing bridge number 73 and 96 with a single structure. So just a little background on the existing bridges. Bridge 96, it was built in 1970, 600 feet long. In 2013, it required an emergency full superstructure replacement due to deterioration from corrosion. Bridge 73, it was built in 69, 1,400 feet long. It's posted, structurally deficient, and then this has the swing bridge. So this bridge can, routinely have mechanical issues, be shut down to boat traffic. The community is heavily involved in the fishing industry, and so having that navigational channel blocked can cause issues for them. So basically within these bridges 40 to 50 years of age, they're already experiencing significant corrosion. We've had to replace the superstructure on one. So in looking at the development of a replacement project, the idea of using an FRP that is corrosion resistance really is why we honed in and identified this project as a great option for GFRP and CFRP. Here's some photos of the existing structure. The bottom 2 are the substructure from the swing span, and then the top 3, those are the cord slabs from the Bridge 96, which that was before the superstructure replacement. So you can see we've gone in there, we've tried to make some repairs. They work, and then if it's not long afterwards, we're still having to go back and provide maintenance. Give you more details about the Harkers Island project itself. The new bridge, it'll be 3,200 feet long, 28 spans. As I mentioned, the girders and the piles will be using the CFRP, 115 girders. 44 of those girders will be 72-inch fibs, Florida I-beams. 56 of those girders will be the 54-inch Florida I-beams, which they're 100 feet long, give or take. The 72s, I should have said, are 130 feet. We've got 3 spans of the 78-inch fibs, and that'll include a channel crossing where we have a 165-foot girder. So the let date was July of 21. Expected completion is 25. The contract amount was just under $60 million. Going back to the linear foot, so we went through and figured up how many once the project is complete of CFRP and GFRP. So right there you've got 100 or 1 million linear foot of CFRP in the girders and the piles, and then close to that same amount with the GFRP with the substructure and the superstructure. The photo there, that was taken earlier this month just to kind of show you the progress that the contractor made in the first season. So you see the new bridge obviously on the left there with the work trestle. I do need to mention the moratorium, so that was a big constraint for the contractor, is there's no in-water work between April 1st and September 30th. So again, the project let in July. The contractor was able to start in-water work October 1st. So you can see from October 1st to March 31st, the contractor was able to pretty much install all the 24-inch pre-stressed piles from the invent 2 side out to the channel. And that ends up being 141 of the 212 piles. And so again, just showing kind of what the bridge layout is going to look like. It will feature a navigational channel with a 120-foot, 5-foot horizontal clearance and 45-foot vertical clearance. The typical section there, we've got a 32-foot clear roadway, 34-foot 7 inches out to out, 4 girder system. Since we do get to when we do get to the channel span, because of the length, we've had to go to a 5 girder system with those 78-inch fibs, but the remaining spans are the 4 girder systems. The division requested that all the low-level spans provide a minimum of 8 foot of vertical clearance just due to wave action. And so just kind of looking at the FRP manufacturing process, I don't know how many folks are familiar with it, but we'll just walk through it. So FRPs are manufactured through a process called pultrusion. The process starts as continuous fibers of either carbon or glass are pulled through a resin bath and saturated. And then as the wet fibers are aligned and pulled through a shaped mold, which is heated, and that cures the resin. And so that's, to note this manufacturing process is one reason you can't field bin FRPs. And so as a designer, as a developing plans, that's really something to consider, that, all this manufacturing has to be done in the plant. There's no, if there's any kind of bars that show up out of spec, there's nothing that the contractor can do, so just something to be aware of. Again, it's really not a direct substitution. It's not a one-to-one on FRPs and conventional steel. The biggest thing is really the modulus of elasticity. The graph there is just your typical stress strain diagram. The gray line is your steel rebar, and the pink line is your FRP, GFRP bar. So you see the steel, as you apply load to it, it'll eventually yield, and at that point, after it yields for a while, then it'll rupture, whereas the GFRP, you're able to apply that load, and as it continues to increase, it's a brittle failure, so there's no yielding of the bar. But that's not to say that there's no ductility in the bar. So the picture there with the 2 gentlemen, it just shows that even though the modulus is much lower than steel, there still is ductility that's available. So just a comparison between GFRP and steel reinforcement. You notice the guaranteed tensile strength for FRP is much higher in most cases. You do not have the yield strength, as I mentioned, and then really keying in on that modulus is basically a quarter of what steel is. I will point out the unit weight, which is, if you look at that number 8 bar there, it's 0.73 pounds per foot for a GFRP bar versus the 2.67. So as you can imagine, a 60-foot number 8 bar is going to weigh roughly 160 pounds, whereas that same bar in GFRP will be 45 pounds. And so just showing some of the pictures from the site there. Those picture on the left is our column reinforcement for the pile footings on bents. Top right picture there is a bent cap that's tied up, and the bottom picture are the stirrups that are used for the pre-stressed girders. And I'll mention that, so you see black bar and white bar. The black bar is, through the manufacturing process, is what the bent bars are. So any black bar you see, that's a bent bar, whereas the straight bars are the white bars. A couple of bent caps, that reinforcement that are in place, ready for side forms and concrete. Again, it's not a one-to-one substitution, so you do end up with a fair number of more bars with GFRP, but discussing it with the contractor, he increased his slump, really has not had any issues so far with pouring, no issues with honeycombing. So as long as we're aware of what we're getting into, it seems that it's gone very smoothly with pouring. So just some considerations when you're detailing your bars. Left photo there. The bar bends are slightly different than what you have with conventional steel. The radius tends to be a little wider. So as you're placing your longitudinal bars, you just have to be aware of how that will line up with relation to those bends, particularly for the pre-stressed girders, the confinement bars. For us, we lost some strand locations because of those bends. The center photo there, that's of a stirrup that's used for the bent caps. So as I mentioned, with the protrusion, they have to do all the bends before the resin cures. And so another constraint with that is that all the bends have to be in the same direction, which limits your shapes. And so that top photo there is if you're trying to achieve a bar with bends that go in opposite directions, you're going to have to use multiple bars to achieve that shape. And then the photo on the right there, that's the bottom mat of one of our footings. Again, one of the limitations with the FRP is the amount of leg length that they can bend. And so I don't know how well you can see that, but the black bar, the L-shaped bar, it only goes a certain length before it's spliced on with the white longitudinal bar that runs full length of the footing. So again, you've got to take those considerations. You're obviously losing your clearance between bars once you factor in the splice location. And also, so all these, and the footing here are number 8 bars. That's the largest bar that the industry can bend at the moment. Again, this technology is changing, so that was, when we developed the plans, that was the constraint that we had. So not to say that maybe they can bend larger bars now, but that's one challenge that we had to overcome. So looking at the comparison between CFRP strands and steel strands, noticing the guaranteed strength, that's 339 KSA versus the 270, and that has since increased quite a bit. So if you factor that in, it's basically a guaranteed strength of 60 kips for a 6/10 CFRP strand. Notice the modulus is slightly lower. The knockdown factor for AASHTO is lower for the CFRP, and so your allowable pull strength there is basically slightly lower. As I mentioned, the guaranteed has since increased, so it's definitely more comparable, but there's still other factors in the design that have to be considered. We've partnered with NC State to do the QA/QC on the material testing for the project, and the guaranteed is listed at 60 in this case, but pretty much all the strand that they've tested is breaking right around that 80 kip mark. So very conservative. So here are a couple of photos of our girders at the pre-stress plant. One thing I'll point out is the coupler system. So with the CFRP, you can't grip those like you would conventional steel. If you put the wedges on, it'll just crush it. So you basically have to splice it with a steel strand, and in doing so, you need these couplers. And the best way I've heard it defined or described is really just like a Chinese finger trap is how it's splicing those two together. And you'll notice here on the picture on the left there, so for a girder, you have a fair amount of strands in the bottom of the flange, and so the precaster has to stagger those couplers, because otherwise if you had them all at one location, you'd be it just wouldn't be possible. And so that's one thing that, needs to be considered as they're laying out their bed. So here are some more photos of the girders. One thing for this project, we really didn't want any ferrous material in the girder. And so we did make a compromise. We allowed them to use stainless steel lifting loops. But one thing that the precaster did request was to have some just courtesy strands to tie the GFRP stirrups to. They were concerned that you tie the stirrups directly to the CFRP, it could put a potential fair amount of weight on there, and then they were concerned that it could potentially rupture the strand. And so it's not very clear, but in this photo, you see those wood blocks on top of the headers. So what the precaster decided to do, he ran some steel strands above the header and actually tied the stirrups onto that, and so it worked out to where he could get his correct projection above the girder. So that was one way he overcame that challenge. And then the photo on the far right there is just the completed beam. So just showing a couple of photos of the current construction. Again, these were taken earlier this month. Right here you're looking on the left at Bent 9, looking up station. Photo on the right, you're looking at span Z. Contractors in the process of forming up the deck, and hopes to pour the first spans in the next couple of weeks. So as I mentioned, this is a corrosive site for us. Typically we would have precast, pre-stressed deck panels for the formwork, but we went with a lightweight deck in this situation, and so the contractor's using removable forms. So there you see, I think they've set 7 spans of girders so far. Bents 8 through 14 there on the bottom. And so it's just really impressive what the contractor's been able to accomplish in the first season. I think it's important to note that, these materials, they're new, they're different, but the contractor's still able to carry on, meet schedule, and really has not had any significant delays due to the material. Especially even from the pile driving. Once they started driving pile, comment was, it's no different than your conventional pile. So I'm going to spend the next few minutes talking about lessons learned so far. So speaking of piles, one thing we learned is you have to consider the Hoyer effect, and those aren't familiar with the Hoyer effect. It's basically as you stress that strand and then relieve it, it tries to return back to its original diameter. So, you stress it, it necks down, relieve it, it tries to return back. And so the first few piles that were driven, the contractor had a short window. He didn't get the project till July. So they immediately started casting piles, get them to the site. And so October 1st, they started driving. And the way his template was laid out, if we had any battered piles, they had to go ahead and cut them off. And in doing so, once they cut them off, you see there, cracks started forming. So that was very alarming for us, and really we weren't quite sure, what to do about it. And so going out and actually looking at it, the cracks conveniently were within the first 2 feet or so, 2 to 3 feet, which is the transfer length, and that was what ends up being embedded in the bent cap. So we felt comfortable. The cracks were solid. There really wasn't any structural concerns. But the interesting fact is that as they progressed, again, these piles were 3 months old, something along that line. But then later on in the season, once the moratorium was over, or it was the moratorium, excuse me, and they were going back and cutting the plumb piles, the photo on the right, you can't see too well there, but there's no issues, no cracking, no recess of the strand. And so these piles were, at this point, 6 months old. It is 10 KSI concrete. And so it really, looking forward to maybe the next project, or even the island side of the channel, those piles, if there's some way to constitute a waiting period, would be, from what we've seen, would be a good idea, because you really don't have any of that cracking issue. So that's something we're going to continue to monitor. And so speaking of the Hoyer effect, we had this happen, and then several months later we had our first girder casting, and so we really should have considered that. And so they cast the first 3 girders, and this is what happens here. For our typical steel strand configuration on our bulb tees, the 2 exterior strands are outside the confinement bars. And so in this case, we went along with that similar strand pattern. And as you see, it busted off the end section there. Again, it was 2 or 3 feet. I mean, the crack did continue, but it was fairly solid. So what we ended up doing, bottom right picture there, we made sure that we bring those strands inward of the confinement bars. And so since that time, we've had no issues with those types of cracks. Some more lessons learned from the girders. So the picture on the left there, that's the 54-inch fib. We've got 2 strands in the web. We've got cracks that are forming along the web face, again 2 to 3 feet. And then on the right there is the 72-inch fibs with web splitting. One thing we've done is we've increased the debond. We've debond those strands in the web on the 54s 2 or 3 feet. That's really done away with that cracking. We've increased the debond on the 72s, and we're still getting some cracking, but it's certainly minimal compared to what we were getting those first few castings. All right, and then the last lesson learned, and it's not so much for the designer or the bridge engineer, but more so for our M&T inspectors as well as the precaster. So with casting the pile, in order to get the economy out of their beds, the precaster ended up with a lot of short sections where the steel strand was basically right at the end of the form. So again, you see the couplers there for the piles, but you notice in those photos, you really only have 2 or 3 inches in some cases, and in some cases 10. I mean, certainly there were situations where they had much more to work with. But so one thing that we had an issue with during the first few castings is that as they were detensioning the beds, all of a sudden, all of the strands would spontaneously detension themselves. And so, you know, certainly a concern there, and I've got a short video I hope we'll play. How do you play? Where's the mouse?
Cables popping by themselves. Whoa. Cables popping by themselves.
So there you can hear the strands starting to go.
Cables popping by themselves. Cables popping by themselves.
And so it sounds like he's seen this happen a time or two. This is not the first time it's happened. So that's just something we're going to continue to monitor. I mean, certainly it didn't happen with every casting, but just something that we're going to have to keep an eye on. We've not had that issue with the girders, but the next set of piles will be interested. Real quick, if anyone's interested, there are some great codes, references that are available through AASHTO, ACI, some research projects. Definitely want to mention Michigan, Florida, and Virginia DOT were instrumental in our plan development. Great resources. And so I'll just leave you with this photo. This was from earlier this week. The first 72-inch fibs were delivered to the site, so they'll start setting those. But with that, again, I appreciate the opportunity and look forward to to this project's completion. So thank you.
Thank you for the presentation, Trey. I'm just curious how you plan to take this project and then possibly implement it into policy for NCDOT structures.
So really, I mean, the benefit we see, the biggest benefit is for the substructure. Anything that's in the corrosive environment, really getting exposed to the chlorides. And so I really see we've got some projects that we're trying to identify that are, relatively forthcoming to use this in the piles and the bent caps. We've really not looked at girders in the future. I mean, certainly that'll be an option, but we really see the benefit in the substructure.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.